Hi everybody. In this video, we are going to be finishing up our very last topic. So it was our graphing linear equations topic, but we are finishing up part 2 of that. So in the previous video, we were actually working on the graphing linear equations, and now we are going to finish up the topic by identifying whether ordered pairs, like particular ordered pairs, are on the graphs of a linear equation. And so that's called like we're looking at, are those ordered pairs solutions to that equation? And so we're going to talk about different ways to determine that. And then on the next or the last couple of pages of notes, we're going to look at some word problems. So we've got, this page and one more, and that will wrap up this topic. So ordered pairs as solutions. So first to fill in here, we're going to fill in the word every. Every point on the line is a solution to the equation that graphs that line. So that's saying that if we've got our line, every point, every ordered pair that lies on the graph of that line is going to be a solution to the equation of that line. And so the question is, like, even on this first one, it's saying, okay, how about the equation y equals 2x minus 7? Does the point 2, -3 lie on the graph of the line? And so we could definitely go and graph it. And that's what this paragraph is talking about. Like, we can go and, graph that line and then see if the ordered pair is on the graph of that line. But sometimes that's a little bit trickier to do because maybe we don't have graph paper. It takes up typically more space. The other thing we can do is just substitute the ordered pair into the equation. And if the left-hand side equals the right-hand side, then what that tells us is that this point lies on the graph of the line, because guess what? Every point on the line is a solution to the equation that graphs that line. So what that means is if we plug it in, left side equals right side, that means that point lies on the line. If the left side of the equation does not equal the right side of the equation, then that ordered pair does not lie on the graph of the line. Like, it could be a point over here. And so if we plugged in this ordered pair here into the equation for this line, the left side would not equal the right-hand side because this ordered pair here does not lie on the graph of the line. All right, so let's check these out. And you're more than welcome to pause the video and then you guys just go through these and then, check the video out, watch me on fast forward and see how you do on these. All right, so here we go. We are plugging it in. So I'm plugging -3 in for y. So -3, does that in fact equal 2 times 2 minus 7? So then I get -3, does that equal 4 minus 7? And I can see right now we've got -3 equals -3, check. So this is the one time I'm going to write out this big long statement, but this is yes, or a true statement. So this is a true statement. Yes, 2, -3 lies on the graph of the line. And the rest of them, I'm just going to say yes or no. All right, I'm going to bump over here to number 4. So this one I've got 11 times 0 plus 4. Does that in fact equal 4? Well, we know 11 times 0 is 0 plus 4 equals 4. 4 equals 4, check. This one is yes. So yes, 0, 4 would lie on the graph of the line. Or you could say true. Either way. All right, let me check number 2. So here I'm going to be checking -1 and -6. So I've got -6 times -1 minus a -6. Is that going to equal 0? So here, negative times a negative is a positive. And if it was just 6 minus 6, that would be true. But we're going to have negative, and then a negative is a positive. And so 12 does not equal 0. So this one is no, or you could write false. So no, and it's no, -1, -6 does not lie on the graph of the line. All right, I'm going to try number 5. So we're going to do 1, this one equals -1, and false. 1 never equals -1. So this one is no. I'm going to try number 3. So we've got 5/2. Is that going to equal 6 times 1/3 minus 1/2? And so this is, I'm just going to change this into 2 1/2. 1/3 of 6 is 2, or you could do 6/3, which is 2, minus 1/2. And so this is going to be 2 1/2 equals 1 1/2, and false. 2 1/2 does not equal 1 1/2. So this is no, or false. And then number 6, we're going to have 4 times 4 plus 5 times -2. Does that equal 3? So 4 times 4 plus 5 times the -2. So we've got 16 minus 10. Is that going to equal 3? 16 minus 10 is going to give us 6, which does not equal 3. So this one is also no or false. All right, which table or tables of values could be generated by the following equation? So I've had students before say, do I need to solve this equation for y first before I plug things in? No, you don't need to do that. You do need to check an ordered pair. And if one ordered pair works, then you need to check at least one more. So you need to check at least 2 points if the first ordered pair works. So if the first ordered pair works, try another ordered pair. If the second ordered pair works, then you get to say, yes, that table works. But why is that? Like, why is it that if one works, why can't we just say, yes, the table works? And the reason why is because if one ordered pair works, what that tells us is at least 1 point lies on the graph of the line. But let me show you something. So if we had 2 lines like this, they intersect at a single point, right? So though, I'm going to put line 1 and line 2. So though line 1 is a totally different line, it's got a totally different equation, and as compared to line 2, they have at least one ordered pair that's going to match in their equations. And so that's why you have to check more than one ordered pair. So if one ordered pair works, you could have just found an intersection point. And so you've got to check one more. However, if you check a point and it doesn't work, so if you check 1 point from a table and it does not work, then you do not have to check anymore. So if 1 point fails, then you get to move on and say that table does not perfectly match the equation. Let's move on. All right. Ugh. So what I like to do on these, I actually like to check if there's any intercepts, an X or a Y. I like to pick those because it's pretty easy to plug in a 0. And so on this one, I'm checking 2 times -5 minus 5 times 0. Does that in fact equal 10? So here I'm getting -10 minus 0 equals 10, -10 equals 10. That is not true. So it's definitely not going to be the first table. So let me check. I'm going to check this one. So I'm going to do 2 times 0 minus 5 times -2. Does that equal positive 10? So I get 0, and then a negative times a negative is a positive. And I get 10 equals 10. All right, so there's one that works. I need to check another point. I'm going to go ahead and do this 0, 5. So I'm going to do 2 times 5 minus 5 times 0. Does that equal 10? Well, this is 10 minus 0 equals 10. And guess what? It works. So 10 equals 10. So this table works. And let's see if this one over here is going to work. So I'm going to do this 5, 0. And so I'm going to do 2 times 0 minus 5 times 5. Does that equal 10? And here that's going to go to 0. So then I'm going to get -25 Does that equal 10? No. And so that one doesn't work either. So the only one that works is table B. All right, let's check some word problems. So application problems for linear equations. Excuse me. Eileen drives 20 miles from her house to the train station, and then she boards a nonstop train to New York in the opposite direction of her house. So we've got house, and then we've got train station, and then we're going to New York. So we go from our house to the train station, and then train station to New York. Eileen drives 20 miles from her house to the train station, and then she boards the nonstop train to New York, and the train travels 55 miles per hour for the entire journey. So first, what we're asked to do is to define the variables. It says define the variables needed for this problem. And so what I want you guys to think about is like, what would be along the X value? What would be along the Y value? Like, what are the two variables that we're thinking about? And I'm thinking about how we have like hours or time and distance. So we have time and distance. And so the amount of time is affecting how long we've traveled, right? So like if we do time down here, time is hours, however long we've been traveling. And then up here would be distance or miles. And so our distance depends on how long we've been traveling because we're going at a nonstop rate of 55 miles per hour. So here I'm going to say, we're going to say X is going to equal the number of hours she travels. And Y is going to be the total distance. From her house. And if you wanted to, you could have totally picked like T equals time or the amount of hours that she travels, and then D equals distance or something like that. All right, then we're to write an equation to represent this situation. Well, if Y equals the total distance, we're saying Y equals, what's our slope? What's our rate of change? Because again, think about this. We're trying to do Y equals mx plus b, right, for our linear equation. Well, what's our rate? It's 55x, because it's times however many hours we're traveling. But then where did we start? Once we did the 55 miles per hour, how many miles did we already start? Like what would be our y-intercept? And it should be 20. So we'd already traveled 20 miles from our house. So it's like this. And then we hop on the train, and maybe the train is going slower than what we were doing. But anyway, that would actually be called a piecewise function if we were doing it that way. But here we're doing, we're going on at 20 miles. That's how far we've gone. And then we're continuing on at a 55 mile per hour rate. And that's what our graph would kind of look like. And so we've got 55x plus 20. So here's our equation. And then where it says, after 2 hours on the train, how far is she from her house? So if we're plugging in, so it says 2 hours, we're plugging 2 in for X or for Y? Well, it's asking how far is she from her house? So that means we're looking for distance. And so we want to take the 2 and we're going to plug it in for the X. So we're going to have Y equals 55 times 2 plus 20. And so that's going to give us 55 times 2 should give us 110 plus 20 is going to give us 130 miles total that we've traveled. All right, so then letter D. About after how many hours on the train will Eileen be 300 miles from her house? So this time we are looking for the amount of hours. And so we're going to plug the 300 in for Y. So 300 equals 55x plus 20. So now let's solve for x. We're going to subtract 20 from both sides. And we're going to get 180, or not 180, 280, sorry. 280 equals 55x. Then we're going to end up dividing both sides by 55. And so 280 divided by 55. I don't have my calculator handy with me. My phone's over there. All right, let's punch in 280 divided by 55. And we are asked to approximate. So look in your calculator and find out x is approximately, it's looking like it should be approximately 5. Approximately 5 hours. You can just pause me for a second. All right, I'm going to find out what it is more closely. So we've got 280, and we're dividing it by 55. And it was 5.09 repeating. Okay. So x equals 5.09 repeating. And so again, it's just after 5 hours. So just after 5 hours, this is what you should have been getting in your calculator. And then you're approximating, it's about 5 hours. All right. Next one, it says Morgan is buying a laptop for $1,080 to use for school. Morgan is going to use the computer store's finance plan to make this purchase. She's going to pay $45 per month for 24 months. She wants to know how much she will still owe after each month of the plan. Define the variables. So what are our two variables we're thinking about? I see us talking about money and again, our time. And so this time I'm going to say T is equal to total money owed, because we're figuring out a payment plan, right? Like how much do we still owe after each month? Or you could do like D for debt. That's probably a better variable, D for debt. And then so I'm going to do that. I'm going to do D for debt. So that'll help me remember. And then I'm going to do M for the number of months. Number of months she has paid. All right, so think about like how at 0 months, how much does she owe? At 0 months, she owes, because she just bought it, $1,080. Well, what's our slope? How much are we changing every single month? We're going down by 45 bucks per month. So we should be going down by 45 bucks per month. So this is like 45 over 1, 45 over 1, and that's 1 month, 2 months. And then I'm going to draw a little break in my graph. And then over here at my x-intercept, how many months have gone by? And it should be 0. So it should be 24 months have gone by, and I owe $0. So okay, let's come back over here. Let's write our equation. So the total debt that I owe would be, you can think about subtracting, like we're taking off $45 per month. And what did we start at? What's our y-intercept? At 1,080 for that. So how much does she owe after 8 months? How much does she owe after 8 months? So we're saying debt equals negative 45 times 8 plus 1,080. Looks like we should be getting negative 360 for here plus 1,080. So after 8 months, she is still going to owe $720 for her laptop. So we're getting closer on getting to 0. And then if she's like, well, at what point in time, how many months have gone by when I actually owe 925 or close to it? So 925 equals negative 45x plus 1080. And so now let's subtract. So we're going to subtract 1080 from both sides. And we should get negative 155 equals negative 45x. Let's divide both sides by negative 45. So that ends up being x equals 31 over 9. And so if we're saying, okay, well, about like, where's that going to be? So 39 divided by 9, how many times is it going to go in evenly? So it's going to be 4 months for 36. And then we've got 3 left over. So that's approximately 4 1/3. And then think about like, okay, when is it going to be 4 1/3 months? 4 1/3 months. Let me put that on there. Is our answer. And let's go back, and it says, when does she owe $925? Well, I think this is somewhat of a trick question. So when does she actually owe $925? Well, she never owes $925, but she's going to owe about $925 in that 4 1/3 months. So between, I'm going to say between 4 and 5 months is when, again, she's approximately. And I'm pausing on this one because it's also kind of a trick question, because when does she ever actually owe $925? Well, she doesn't ever actually owe $925 because that's not one of the numbers she owes. That's not going to be the number that's on her payment plan, right? But she's going to owe approximately $925 in between 4 and 5 months. So I guess it depends on how picky you want to be on answering this question. All right. Let's go to the next one. Number 3, it says Warren has $10 saved when he begins babysitting. He charges $12 an hour and he is trying to save up enough for a new saddle. Define the variables for this problem. So again, we've got Warren has $10 saved. So we've got our $12 an hour here, $10 saved, and he's trying to save up enough for a new saddle. What are our kind of 2 variables again? And we've got one, again, money, and then what was our other variable? It's like the time, like how many hours have we worked? So our variable, I'm going to say M is money saved. And then T is number of hours worked. Is what we're going to say. Okay. And he's trying to save up enough money for the saddle. So here we go. M is our total money. So again, thinking about like time. And here's our money. So again, that's why over here, M is going to be for our money, for where our Y is. This is our Y axis. And then what's our rate of change? How much are we changing per hour? It should be 12. So we've got 12x, and then did we start with any money to begin with? Yeah, we started with 10 bucks. Not a bunch, but it's better than nothing. All right. So when will he have $400? So at what point will he have $400? So let's put 400 over here equals 12x plus 10. And we're going to subtract 10 from both sides. We're going to get 390 equals 12x. Divide both sides by 12. And x, let's see, if we are simplifying that, looking like it's coming down to 63 over 2. And then what is that? That's 32 and 1/2. So when will he have that? Well, again, think about like, okay, what did X actually represent? It's the total number of hours. So he will have that amount after he's worked 32.5 hours. So after he has worked 32.5 hours is when we will have at least $400. All right, the next one, it says, after 26 hours of babysitting, Warren's uncle gives him 50 bucks. Does Warren now have enough for the $400 saddle? All right, so let's do 26 hours of babysitting. So we've got, right in our equation again, we've got 12x plus 10. And we did 26 hours, or he did 26 hours of babysitting. We already had the 10. And then Warren also gives him 50 bucks. So we are going to add this. So it looks like 12 times 26, I've written that part down, is 312 plus 60. And then we've got 372. Does he have enough for the saddle? Not quite yet. So not quite 400. Almost. All right, let's check out our fourth and final example. Woo, woo. All right, Charlie is sketching pictures of their friends for the holidays. They spend 30 minutes gathering supplies, and the sketches take them 4.5 hours each to complete. Define our variables. So again, sketching pictures of their friends for the holidays. They spend 30 minutes. There's 1 minute gathering supplies, and the sketches take them 4.5 hours to complete. So we're talking about like number of sketches and the time that's elapsed. So let's do this. We're going to say X is equal to number of sketches they draw. And then let's do Y is equal to the amount of time spent on the project. So including like the time it takes you to gather up the supplies plus the time it's taking for each of the sketches. All right, so it says write an equation to represent the situation. So we're going to say, well, what's our total time, which is going to be Y. So we're going to say Y equals, and I forgot to label this over here, so number of sketches. And this is like total time over here. All right, so Y equals, what's our rate of change? Our rate of change is 4.5x by however many sketches we do or we are taking care of, plus the 30 minutes it takes us to round up the supplies. Let me see. Oh, one thing I want to point out. I just noticed this. We are at 4.5 hours. And we are talking about 30 minutes here. So I actually need to change this. So we're either going to change this into minutes or hours. And I think an easy way to do that is to take that out right there. 30 minutes is how many hours? It's a half an hour. So we want to switch that so we're talking about in the same unit. That would have messed up our answers if we wouldn't have caught that. The other thing you can do is you can say, well, 4.5 hours is how many minutes? And you could have written it like that too. So we could have done, or Y equals 270x plus 30. So this one again would have been in minutes, and this one is going to be in hours. And so that's fine. Let's actually keep them both there because let's see what they ask us for down here. And then that might be dependent on which equation I choose based on, what our unit of measure is for these. So it says Charlie plans 22 hours to work on the project. How many sketches can they complete? So we've got 22 hours over here. And because it's hours, I'm going to use this equation. So it's 22 equals 4.5x plus 0.5. I'm going to subtract the 0.5. And we are going to get 21.5 divided by 4.5x. We're going to divide both sides by 4.5. And then this one I have written down. We end up getting x equals 4.7 with that 7 repeating. And then again, go back and see what it asks you. How many sketches can they actually complete? Well, that's only partial of a sketch. So that means we're actually going to round down and we're going to say Charlie can complete 4 sketches for that. All right, let's look at the last one. Charlie decides to rearrange their schedule so they can finish 6 sketches. How long does it take them total? So this time we're going to say y equals 4.5 times 6 plus 0.5. And then when you're multiplying that out, again, take your calculator, do 4.5 times 6 plus a half, and we should end up with 27.5 hours to do all of those. And that is it. That's the last example for our notes packet. Thanks for tuning in.